Hey guys, so in this video, my goal is to kind of talk about the inner product, right? How we've talked about the inner product in terms of the vector spaces that we did in section 2, and expand that idea to cover the function spaces that we've been covering in the last few videos. But before I do that, I want to take a minute to I want to take a minute to clarify a few things that I talked about in the last few videos. Um, and the first thing is about the delta function, right? And I talked to you about how phi a of x, right, which is the wave function with a definite value of position being a, x equals a, how this wave function is delta of x minus a, right? And I tried to make that make intuitive sense, and it does make sense to an extent that if we had a wave function with a definite value of position, it would look something like this, right? But why specifically would this peak be infinite? Why would it have that, why would it be precisely that delta function? And the answer, that and I've been thinking a lot about this, and the best answer I can really give is that the pioneers of the quantum theory, the guys that came up with this, knew what they were doing, and they knew that this delta function would end up. They were very familiar with the math of it, and they figured out that the delta function would be really really useful in this context, and that it was actually the right function to pick. So for right now, I'm going to ask you, if you don't fully understand this, and I really hate doing this, but with a few things in quantum mechanics, I don't think that there's really a way around it of just saying kind of trust me on this, and everything's going to kind of come from it. It's all going to fit together because we have this choice of function that we made. And you will hopefully see soon why this function is as useful as I say it is. The next thing is about the units and dimensions of the wave function, right? Because we always talk in physics about units and dimensions, right? And so what about for the wave function? Well, we're going to investigate this by looking at the equation for probability, right? The probability to find a particle between x1 and x2. We know this is the integral from x1 to x2 of psi norm squared dx, right? Because this is the probability density, right? And so if we look at probability, this is no dimensions, right? Probability is really just a ratio, right? If it's if say you have 10 apples and two of them are green, right? And you want to know the probability of picking a green apple, it's two green apples over 10 apples, right? The units of apples kind of cancels out. Probability is a ratio, right? Just like the trig ratios, it has no dimensions, right? Well, we remember this integral does not have dimensions on its own. This dx, though, this dx has dimensions of length, right? Right, which would mean that in order to have this probability have no dimensions, psi squared would have to have dimensions of 1 over length, right? And so if the dimensions of psi norm squared is 1 over length, the dimensions of psi must be 1 over the square root of length. Right? And so theoretically, yeah, you could measure psi in like 1 over the square root of meters, or meters to the negative 1/2, right? But nobody actually really does that. I've never seen that done. So there's the units aren't extremely important, but it's always good to know that there are units, and knowing what the dimensions are. We aren't going to be really using them much, if at all, in this course. So one last thing, and this will sort of tie in to what I want to do in the rest of this video, right? So the first thing is we've talked about this superposition, right? The wave function. Psi is the integral from negative infinity to infinity, right? The integral over all possible values of some observable q, right? And this is c sub q of phi sub q of x dx, or sorry, not dx, dq. And I just want to show you that this is going to give us a function of x. And the way I'm going to do that is I'm just going to use a basic integral example. So I'll just do this to the side here. If I have some integral, right, from, I don't know, 0 to 1 of x t squared dt, right? Well, we know when we're calculating an integral like this, and it turns out when there's multiple variables, but you're only integrating over one of them, this x acts as though it's a constant, right? So this can get taken out, so this is equal to x times the integral of 0 to 1, from 0 to 1 of t squared dt, right? And so this would be x times, this is t cubed over 3 from 0 to 1, right? And then if we plug this in, 1 cubed is 1 over 3 is 1/3, 0 cubed is 0, right? So this would be 1/3 x. So what I want to point out to you is that we have an integral here where we have a function of x and t inside it. We're integrating over t, and our answer is in terms of x. When we're integrating over this t, it's like summing over the t. When we're doing that sum, right, of the wave functions, when we have c sub j, phi sub j, right, when we're doing that sum over all possible values of j, j is just our counting index. It's not actually a variable that's significant, or the variable j does not appear, right? If we define each of our c sub j's and our phi sub j's, that variable j doesn't end up appearing in our answer. It's just like here, we're taking just a big sum, right? So when we're doing this, we're summing over all possible values of q, right? And here we have c sub q is a function of q, phi q of x is a function of q and x, right? Because it's a function of x, it's a wave function. That also note that each phi, because it's a wave function, it would also have units of 1 over root length. But this is a function of q and x, right? And we're taking the integral over q, so we'll be left with a function of x. Right? Okay, and so now, talking more about this, the superposition. All right. So let's look at what we've done in position, in vector space, in the vector space that we did in section 2, right? So if I have two vectors, I've got u and I have v. Right? And u, this will be u1 phi 1 plus u2 phi 2 plus dot dot dot, which is, right, we can just write this as the sum over all possible values of j of u sub j phi sub j. Right? And you can sort of see that j is no longer in this. J is just sort of the variable. It's called a dummy variable, actually, or a dummy index. That we're just summing over all possible values of, right? Same thing with v, right? This is, sorry, not u, but this would be v1, phi 1, plus v2, phi 2, plus dot dot dot, right? This is the sum over all possible values of j, v sub j, phi sub j. Right? And now, if we want to take the inner product, well, we know how to do that. If we want to take the inner product of u and v, right, this is u1 star v1 plus u2 star v2 plus dot 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 plus, which is equal to the sum over all possible values of j of uj star vj. right? And so now let's generalize this into function spaces, right? How can we define an inner product in function space? Okay, so let's take, well, we've got psi1 of x, right, which is the integral over from negative infinity to infinity, right? This is just the same thing. It's just a sum over all possible values, except now q, our observable, is a continuous quantity, right? So this is of C1A, right? Instead of just using Q, I'm going to write this in the position basis. Now, here's the key thing. Remember that we can express psi in whatever basis we want to, but the inner product in one basis is the inner product in every other basis. We talked about that back in the beginning of section 2, I think in probably video 2, that we just had to do that dot product, right, in one basis, and like the color basis, right, or the color and hardness basis, right? And then, no, sorry, the color basis. We only had to do the like the dot product in the color basis or the hardness basis, right? Whichever one it would hold. So if we do this inner product in the position basis, it will be the same for the functions no matter what basis we express them in. If that doesn't make sense, you can again just take me on that one. You can show that mathematically. And hopefully it will make more sense to you as you go on. But I would definitely review that video where we talked about the dot product being the same in whatever in whatever basis you're in, right? So you can just use the most convenient basis, and it turns out this is a very convenient basis for reasons that you will see, right? So this is C1A phi of x, right, dx, right? And psi 2 of x is the integral from negative infinity to infinity, just the integral over all possible values of, oh, sorry, hopefully you caught that. This is not x, this is a, dA. Of all possible values of a, C2a, and a, remember, is kind of like position. It's the definite position, right? Phi a is a function of x that has a definite position a, right? C2a phi a of x dA, right? And now, right, let's think about what this dot product would be, or this inner product would be. Well, and I'll do this in red. We can see here, right? The reason that we can do this, right, is because we are in an orthonormal basis. I showed that in section 2 that this dot product works. And again, if you don't remember, go back to section 2, re-look at how we showed that this is what the inner product is, right? As long as the phis are in a, as long as we're expressing them in an orthonormal basis. And in the next video, we'll talk about the orthonormal basis that we'll be using for function spaces, which is a little bit different, and I'll make sure to get to showing you that in our next video. But what we want to figure out some orthonormal basis, right? So that the inner product is the sum, or in this case, the integral of the product of these coefficients, right? Just like these basis states sort of go away in the inner product would just be, right? We could just define the inner product analogous to this one in vector space. It would make sense that it would be, so the inner product of psi 1 of x and psi 2 of x would be the integral from negative infinity to infinity, right, over all possible values of a, right, of C1a star, right, because this is our first coefficient, the product of the coefficients, with that first one being complex conjugated. So C2a, then dA, right? And so this is what our inner product would be. But this is why this is true for any basis, A or any Q, right? This would be C1Q star C2Q, right? But here's the trick with this, right? We know, at least in terms of position, right? At least in terms of position, Actually, I'll start it off with like this. First of all, this is going to just give us a number, right? It's not going to be another function, right? Because I want to show you this. It's really important because this a, right? This a is our dummy variable. It's the variable that we're summing over. We're taking the integral over. It's not going to appear in our answer. So we can just call this whatever we want to call it, right? So from negative infinity to infinity, let's say c1x star, right? Because it's just the same. It's x is the position, right? c2x dx, right? And now, hopefully you can see where I'm going with this. We talked about in the other video how c1x, or really we talked about how cx equals psi of x, right? So c1x would be psi 1 of x, c2x would be psi 2 of x, right? So this inner product can be written, see if I spaced right that here, is the integral from negative infinity to infinity of psi 1 star psi 2 dx, right? The other way we could do this, if this step makes you a little bit uncomfortable, what I'll do, I can sort of do this a little bit of an alternative way. This, right? A is just a position, right? So C1, CA would just, ooh, I didn't want to use that green because I already just used that. Let's go with this color. I need to fix that J in case you weren't done writing that down. So CA, right? CA is psi of A, right? Because we know CA is the probability density of having a position A is CA norm squared, right? And we know the probability density of having a position X is psi of X norm squared, right? So the probability density of having a, right? So the probability density of having a position X equals A, right? Which, remember, we have to remember A is a position. That's why I chose to do it like this, so I could show you the inner product. The probability density of having a position X equals A would just be the wave function at evaluated point A norm squared, right? So hopefully this will make sense to you. CA is psi A. We can do that with any position, right? If we call the position B or C, right? But so the coefficient, right, that probability amplitude we call it, of having a position A is just psi of A, right? So this is the integral from negative infinity to infinity psi 1 of A, that's complex conjugate, times psi 2 of A dA, right? And then, or dA, and now it should be pretty obvious that, right, it doesn't matter what we call this, right? This is the same as just, whatever thing, whatever dx, right? The other way you can look at this is psi 1 and psi 2 are the coefficients. They are right? We talked about that before. Psi is the coefficient, right? So it would make sense that in this inner product, we're taking the integral of the first coefficient, complex conjugate, times the second coefficient. They are the coefficients. They're the probability amplitude, right? And this is how we sort of defined the coefficient up here. Right? This is how we kind of defined what we wanted our coefficients to be. That's what the wave function is, right? We talked about that on the last video, so hopefully that's comfortable. If not, you may want to watch the last video a few times, or not a few times, but however many times it takes for this concept to really sink in, right? Hopefully you were able to sort of follow this. It's a weird argument to make, but and I'm going to erase this, so hopefully you have it down. I'm going to rewrite what we had. It's a little bit of a weird argument. There's a few tricks that we had to use here, but hopefully this makes sense, right? So we know this is the big result from this video. The inner product of two wave functions, psi 1 and psi 2, is the integral from negative infinity to infinity of psi 1 complex conjugate psi 2 dx. Right? And this is, sorry, the one other thing that I want to do in this video is talk about what psi inner product with psi is, right, using this definition. First thing to remember, this works in any basis. No matter what basis we're in, this is the inner product. Remember, I was talking about that earlier. I just want to make sure that sinks in, because this, being able to do and understand this inner product is what everything else that we're going to be doing relies on. Okay, so now psi inner product with psi, well, this is integral from negative infinity to infinity of psi complex conjugate psi dx, right? Well, this is the integral from negative infinity to infinity psi norm squared dx, right? Which is equal to 1. That's our normalization condition. So just like we could in vector spaces, we can define our normalization condition as this. That the wave function inner product with itself is equal to 1, and that is our normalization condition. So these two results are the big ideas from this video. And I will see you in the next video, where we will talk about an orthonormal basis in function space.